We are told that xn converges to x, these are random variables, in probability with respect to probability p, and that f is continuous. And we are asked to show that f of xn converges in probability to f of x. Here f is just a continuous function. The way we do this is via subsequence. So we let x and k be an arbitrary subsequence of xn. And then we know that this arbitrary subsequence converges to x in probability. That just simply follows by the definition of convergence in probability. If the probability of the absolute value of xn minus x being greater than epsilon converges to 0, then certainly the same thing is true for the probability of the absolute value of xn k minus x being greater than epsilon. Hence, the convergence of probability follows for this arbitrary subsequence. Now we know from a result in the notes that when you have convergence in probability, there is a subsequence that converges almost surely. So for the subsequence x and k, which was arbitrary, we take a subsequence from that result in the notes such that this subsequence x and j converges almost surely to x. Then by the continuity of f of x and j converges to f of x almost surely as well. So this is just apply it to where the convergence of x and j is to x, and use first year calculus rules that limits of continuous functions exist when the arguments converge. So we know then that f of x and j converges in probability to f of x because almost sure convergence implies convergence in probability. And so now we can just recap what we stated, that every subsequence of fxn, because we took an arbitrary fx and k, has a further subsequence fxnj that converges to f of x in probability. And so that is equivalent to saying that fxn converges in probability to f of x by our standard contradiction argument.